Imagine for a moment that everything you perceive, everything you see, touch, and experience is not quite as it seems. What if the very fabric of reality is not solid and immutable, but rather just a projection? This mind-bending concept suggests that our entire universe, with all its galaxies, stars, and planets, is encoded on a distant, two-dimensional surface, much like a cosmic hologram, shimmering with information. This isn't just a plot from a science fiction movie. It's a real, legitimate idea that's being actively explored and debated by some of the world's leading physicists and cosmologists. They're grappling with the implications of this holographic principle. The holographic principle, in essence, suggests that all the information required to describe everything within our universe, every particle and every interaction, could be fully described by data stored on its boundary, a distant surface encompassing all that we know. Think of it like a sophisticated video game with stunningly realistic graphics. In that game, you perceive a rich, immersive 3D world, but it's all rendered from underlying 2D code, lines of programming that dictate every detail of your experience. If this holographic principle holds true, then our seemingly solid three-dimensional reality is, in a very real sense, an illusion. What we perceive as depth and substance is merely an emergent property, arising from a deeper, more fundamental two-dimensional source. The genesis of this radical idea emerged from the study of black holes, those enigmatic cosmic objects with gravitational pulls so strong that nothing, not even light, can escape. Scientists observed that information about objects falling into a black hole seems to be stored not inside its volume but rather on its surface, the event horizon. This intriguing observation led scientists to wonder, if information can be encoded on the surface of a black hole, could the whole universe in all its vastness and complexity work the same way? If so, then everything we experience, every sensation, every interaction, might be a projection emanating from the very edge of the cosmos, a distant boundary to our observable universe. It's a truly radical idea, one that fundamentally challenges our most basic assumptions about the nature of reality and our place within it. So if reality, as we perceive it, is indeed a projection, then what profound and perhaps unknowable truths lie hidden beneath the surface of this grand illusion? What is the true nature of existence? The holographic principle at first glance can seem incredibly abstract and difficult to grasp. So, let's simplify the holographic principle with an analogy. We'll use something familiar to illustrate this profound concept. Imagine a library, a vast repository of knowledge filled with countless books. In our everyday experience, you'd naturally assume that its information capacity, the amount of knowledge it can hold, depends on its volume, the sheer size of the building and the number of shelves it contains. The more space, the more books, the more information, right? But the holographic principle throws a wrench in this intuitive understanding. It says it's the surface area, the walls, not the space inside, that matters. The amount of information the library can hold is dictated by the area of its walls, not the cubic footage of its interior. It's as if every book's content, every word, every idea, could be perfectly encoded on the paint covering the library's walls. Every story, every scientific theory, every poem, all contained within the patterns and textures of the wall's surface. In this view, the universe's information, everything that exists, is fundamentally two-dimensional. It's all encoded on a surface. The third dimension, depth, the very sense of space we perceive, may be a cosmic illusion, like a 3D image that appears to pop out from a flat holographic sticker. The depth is there, but it's ultimately derived from a two-dimensional surface. Extending this further, even a USB drive's data limit, its capacity to store information, would depend on the surface area of its components, not its overall size or volume. This means the universe, vast and seemingly infinite as it is, has a finite information capacity set by the area of its cosmic horizon, the boundary beyond which we cannot see. Therefore, our reality could be a grand illusion, projected from a two-dimensional surface at the edge of space and time, much like a movie projected onto a screen. Every particle, every interaction, every thought, encoded on this cosmic boundary. It's a staggering thought to consider that everything we experience is a projection from this distant surface. The universe is like a hard drive with a fixed capacity, a limit to the amount of information it can contain, and we're all part of its data set, individual bits of information within this cosmic database. It's a mind-bending shift in how we think about space, information, and existence, challenging our fundamental assumptions about the nature of reality. What we perceive as infinite complexity, the vastness and detail of the cosmos, may ultimately be written on a cosmic postcard, a finite surface containing all the information of our universe. The story of the holographic principle, a concept that challenges our fundamental understanding of reality, begins with one of the most enigmatic objects in the cosmos, black holes. These celestial behemoths, with their immense gravitational pull, serve as the unlikely starting point for a journey into the very fabric of space and time. Black holes present us with the universe's ultimate information paradox, a puzzle that has baffled physicists for decades. What happens to the information of everything that falls into these cosmic vacuum cleaners? Does it simply vanish, or is it somehow preserved? At first glance, black holes seem to be the ultimate destroyers of information, obliterating everything that crosses their event horizon. But quantum mechanics, the theory governing the behavior of matter at the smallest scales, tells us that information can never truly be lost. This contradiction sparked a major scientific debate. In the 1970s, physicist Jacob Bekenstein made a groundbreaking discovery. He found that a black hole's information content isn't determined by its volume as one might expect, but rather by the area of its event horizon, the boundary beyond which nothing can escape. This was a radical departure from classical physics. Stephen Hawking, another towering figure in theoretical physics, soon confirmed this revolutionary idea. His work on Hawking radiation, the faint thermal radiation emitted by black holes, provided the crucial link. Hawking demonstrated that black holes slowly leak information back into the universe through this radiation, albeit in a scrambled form. This revelation implied that the details of everything that falls into a black hole are not lost forever. Instead, they are somehow encoded on its two-dimensional event horizon, like information etched onto a surface. In essence, black holes act like cosmic hard drives, storing vast amounts of information. They are capable of storing three-dimensional data on a two-dimensional surface, a concept that seems paradoxical at first. This realization was a revolutionary clue, a hint that something profound was at play. It suggested that maybe all of reality, not just black holes, works this way, that the universe itself might be a kind of hologram. If black holes, these extreme objects in the cosmos, employ this holographic trick, then perhaps the entire universe in all its complexity and grandeur does too. The black hole information paradox, once a seemingly isolated problem, became the key to unlocking a radical new view of the cosmos, a perspective that challenges our deepest assumptions about the nature of reality. Our universe, with all its stars, galaxies, and intricate structures, might be a vast projection, with its true information, its fundamental blueprint, written on a distant, encompassing surface. The implications of this idea reach far beyond the event horizons of black holes. They fundamentally reshape our understanding of space, time, gravity, and the very fabric of reality itself. From this cosmic puzzle, the holographic principle was born, emerging from the heart of cosmic mystery and offering a tantalizing glimpse into the true nature of our universe. If black holes store information on their surfaces, could the universe do the same? Physicists Gerard 't Hooft and Leonard Susskind proposed that our entire universe is a hologram, a 3D reality projected from a 2D cosmic boundary. This idea bridges Einstein's relativity and quantum mechanics, two theories that rarely agree. In string theory, the holographic principle shows that gravity in 3D space can be equivalent to a quantum theory on a 2D surface. Space-time itself may be emergent, built from fundamental units of information, like pixels on a screen. If we could zoom in far enough, we'd see reality as grainy, not smooth. The universe isn't a stage, it's the show, projected from the edge. Is there evidence for this wild idea? Some clues come from the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this ancient light match predictions from the simplest holographic models. The patterns in the CMB could be the imprint of quantum fluctuations on a two-dimensional surface, stretched across the sky. While not definitive proof, these findings show the holographic principle fits real data as well as standard cosmology. The idea that our universe began as a 2D structure, later projecting the third dimension, is gaining traction. The CMB might be the screen, and its patterns the signature of a holographic origin. More evidence is needed, but the theory is now testable, and that's a huge leap. The universe's fundamental code may be written in the static of the cosmos. To test the holographic principle, scientists built the Fermilab holometer, a microscope for space-time itself. If space is a projection, it should be pixelated at the tiniest scales, like a digital screen. The holometer used powerful lasers to search for holographic noise, tiny jitters in spacetime. If found, it would be direct evidence that our universe is built from fundamental bits of information. After a year of data, the holometer found no such noise, ruling out the simplest pixelated models. Spacetime appears smoothed down to the smallest scales we can measure. This doesn't disprove the holographic principle, but it forces theorists to refine their ideas. The search for cosmic pixels continues, pushing the limits of what we can detect. Each experiment brings us closer to understanding the true nature of reality. The quest for the universe's pixels is far from over. The idea of reality as a projection is a staple of science fiction, like The Matrix, where the world is a computer simulation. The holographic principle echoes this, but with a crucial difference. It's not about artificial simulations, but nature's own information code. There's no creator or computer, just the laws of physics projecting our world from a deeper layer. Popular culture has primed us to accept these mind-bending ideas, making scientific communication easier. The principle also connects to other wild theories like the multiverse, suggesting our universe's boundary might exist in a higher dimensional space. Maybe there are countless other holograms, each with its own reality. While speculative, the holographic principle unites some of the most profound ideas in modern physics. It blurs the line between what we know and what we can only imagine. Science fiction and science are closer than ever. The holographic principle is the result of decades of work by brilliant physicists. Jacob Bekenstein first linked black hole entropy to surface area, planting the seed for the idea. Stephen Hawking's discovery of black hole radiation confirmed and expanded Bekenstein's insight. Gerard T. Hooft and Leonard Susskind extended the principle from black holes to the entire universe, making it a universal law. Juan Maldacina's ADS CFT correspondence gave the principle a precise mathematical foundation, showing gravity in 3D space is equivalent to a quantum theory on a 2D boundary. Their work transformed a black hole curiosity into a central pillar of modern physics. The holographic principle now guides research in string theory and quantum gravity. It's a testament to the power of bold ideas and relentless curiosity. The holographic principle challenges everything we think we know about reality. If true, our three-dimensional world is a projection from a two-dimensional blueprint at the universe's edge. Clues from black holes and cosmic background radiation point toward this possibility. Experiments have set limits, but the search continues, refining our models and deepening the mystery. If we are living in a hologram, our experiences are still real. It just redefines what real means. Unlocking the universe's code could lead to a unified theory of everything. The quest is ongoing, with new experiments and ideas on the horizon. The universe is still revealing its secrets. Stay curious, and the next discovery could change everything.